Okay, Cape Physics Unit 2 students, welcome back to another video. So we'll be picking up where we left off at item 21, right? And so item 21 is shown here. So here we have this diagram. It's a potential divider circuit. As you can see here, we have this resistor here, and then there's like, a point A here in the middle. And then we have down here, which is just this resistor, 200 ohm resistor that's down here, right? So it's a potential divider circuit, and it's formed above from a thermistor and a 200 ohm resistor, right? So this is just what the diagram represents. And then the thermistor has a resistance of 2 kilo ohms at room temperature and 200 ohms at 100 degrees C. So remember now, a thermistor is a negative temperature gradient device. So that means that whenever the temperature increases, the resistance decreases. So that's what we see here. We see that at room temperature, which is about 20 degrees Celsius, our resistance is 2 kilo ohms or 2000 ohms, right? But once we get up to 100 degrees C, we see that the resistance dropped down to 200 ohm, right? So that's just a little bit of revision about thermistor and how it's a negative temperature gradient kind of a device, okay? All right. So they told us that what the resistance of the thermistor is at different temperatures. And then now they're asking us, what is the change in the potential at A? So at this point, right? What is the change in potential at this point? When we move this thermistor from water at room temperature to boiling water, right? So again, they gave us the resistance value, so we know that the resistance of the thermistor will actually be changing. And so the idea is then as the resistance changes, so let's write that here, as the resistance, right? As the resistance of the thermistor changes, then the voltage is the potential at A is also gonna change. That's the overarching thing here, right? So we need to get into our heads before we approach this question. So as the resistance of the thermistor changes, potential at A will also change, right? That makes sense. If your resistance is changing, the potential at that point will also change, right? So let's just write that down to have that here, that also changes, okay? All right. So they're asking us to calculate the change in potential at A when the thermistor is moved from water at room temperature, where the resistance of the thermistor is 2 kilo ohm, to boiling water, where the resistance of the thermistor will now be 200 ohm, okay? So to do that now, we have to remember our potential divider formula, right? And that's that the voltage at a point, so let me write that. So the voltage at a point A, right, is going to be equal to the total voltage that's flowing through that, which in this case would be 20. So that's V total times the resistor in question. So I'm going to write thermistor resistance as, I'm going to put R therm. So we know that it's the resistance of that thermistor. So R therm divided by R total. So the total resistance, right? So that would give us our voltage A at a point. So this is our guiding formula, right? So let me just box that. Hope you're following along nicely. So let me just box this. So I'm going to box this. This is our formula for voltage at a point A when we have a potential divider. The voltage at this point A will be the total voltage that's coming in. So this 20 times the resistance of the thermistor divided by the total resistance, which would be the resistance of the thermistor plus this one. Okay, so we come down here now. Follow me down here. Follow me down here now, right? So we're right here now. So we're at 20 degrees. So we're at room temperature, right? So we're calculating the PD when we're at room temperature at that point A. So remember now, when we're at room temperature, the thermistor has 2,000 ohms. That's what its resistance is, or 2 kilo ohms, right? That's what they told us in the question. So we're gonna take that 2,000 and add it to this 200 to get the total resistance, right? So RT, so remember now we're working with our formula here. RT is equal to 2000, right? That's for the thermistor, plus the 200 from that resistor that's right next to it. So the RT will be, in this case, the RT will be 2200, right? And so if we come over here now, what we'll see is that I've substituted in all the values now that we know into this equation up here. So our V total is 20 volts. So I have 20 volts here. And I multiply that by the resistance of the thermistor, which is 2000 ohms, divided by the total resistance, which is 2200, because it's the 2000 plus the 200. And we come out with a PD of 18.18 volts, right? So that's what we have for our PD when we are at room temperature. At A, the PD will be 18.18, right? All right. So then now, if we're at 100 degrees C now, right? When we're at 100 degrees C, the resistance of the thermistor is going to change from 2000. So let me change that, right? It's going to change from 2000 now, and it's going to end up being 200, right? That's what the question told us, that no, this is going to be 200 because it's a thermistor. When you increase the temperature, the resistance drops. So the resistance is now 200 ohms when we're at 100 degrees C. And so our total is going to change as well. So let me just adjust that as well now. So this is going to change as well. Let me erase all of that, right? And so now what we have is that we have the 200 from here remaining, and then now we have the 200 for the thermistor here, right? So now our total resistance will be 400 ohms, right? And so again, I'm using this formula, right? So I'm using this formula, and I come down all the way down here to show you my working out. So here we are, guys. All right, so this is my formula. Remember now, the total voltage coming in is 20. So I put my 20 here, and then I multiply that by the resistance of the thermistor, which is now 200, divided by the total resistance, which is now 400. So see it here, 200 divided by 400 times 20, I get 10 volts, right? And so remember, the question was asking us about a change in potential at A, right? So initially, right, when we're at room temperature, our resistance is 18.18. We calculated that here. Now, when the temperature rises up now and we're at boiling point, then the temperature ends up being what? Then the PD ends up being 10 volts, right? So what happened, guys? As we went from 20 up to 100 degrees C, there was a, what was that? That was a decrease, right? There's a fall. There's a fall in the PD, in the potential. There's a fall from what? 18.18 to 10. So there's a roughly, that's 8.18 when you subtract 10 from that, right? And so that's roughly a fall of 8 volts, right? And so when we look here, we see that fall of about 8 volts. So the B is our answer. That's how we ended up selecting B, okay? So again, when you look at a potential divider, whenever you see a potential divider circuit, just immediately think in your head, okay, what's the formula that I have to use, right? And that's that the potential at a point is going to be equal to the total voltage coming in times the resistance of the section that you're concerned about over the total resistance in the circuit, okay? So that's what this is. All right, so we are good and we are ready to move on to part B, to 22, sorry, question 22. So 2022 now says, which pair of values give the open loop gain of an ideal op-amp and that of a typical op-amp? So we're looking at open loop gain. Now the open loop gain of an ideal op-amp, we know that that's infinite, right? We want infinite open loop gain in the ideal case. And for a typical op-amp, what we would observe is a gain of 10 to the 5, right? So when we look in this table, we're looking for the pair that has that, right? Ideal being infinity, and then typical op-amp being 10 to the 5th for our open loop gain. And so when we look here, we see that that fits B, right? B says that ideal op-amp has an infinite open loop gain and a typical gain, and the typical one has a gain of 10 to the 5th. So B is our answer here, okay? That one is not too bad. It's just really recalling what the values are in the ideal case and the typical case, okay? So B is our answer here. And let's go down to 23 now. So 23 is showing us a truth table, right? So we have X, Y, Z. So these are our inputs, and then this is our output that corresponds to these two inputs, okay? So the question reads, which of the following combinations gives the truth table shown above? So this is our truth table, and we're trying to find which of these combinations would produce a similar output, right? Or a similar output when given these inputs. So the answer here was C. So I came up with C for my answer. And the way I did that was like, okay, if we take the first one, right? Let's take this first row of the truth table. And I plug in 0 here, 0 here. This is an AND gate. So because for the AND gate, we need both to be 1, right? For us to get an output of 1. So because they're both 0, of course, I'm going to get 0 here. Then that 0 is going to come into a NOT gate, which is an inverter. So the NOT gate is just going to invert the 0 and I end up with 1 here. So my first row checks out, right? My input of 0, X for 0, Y for 0, and I end up with 1. So that checks out, right? So that's good. So that's what we get there. And then let's try another combination and then we can move on just to show you guys how I arrived there, right? Let's try the combination when I'm putting in, let me put in 0 and 1. So let me put in the second one. So I'm putting in 0 here and 1 here. That's the second row I'm testing, right? So when I put 0 and 1, remember it's an AND gate, so we need both ones to end up getting a 1. So if we have a 1 and a 0, we're going to get 0. And then this is going to get inverted because it's a NOT gate, and so we're going to have 1. So for an input at X of 0 and an input of Y of 1, I'm going to get 1. And so that matches this truth table, so we're good. C is our answer here, okay? All right, so let's clear this. So to arrive at that or to eliminate the other one, guys, you could just test one number. So just test this first row, right, for all of them and see which ones you can eliminate and then move from there. But in the end, we landed on our answer being C. Okay, so we're just matching the combination diagram to the truth table. All right, so let's move over now to question 24. Let's go and do question 24 now. All right, so in question 24, that's this one. So item 24 refers to the following diagram, which shows a non-inverting amplifier, right? So this is key. You have to know what kind of amplifier. It's a non-inverting amplifier and it has negative feedback, right? So it's a non-inverting amplifier because we can see that our input voltage is going to our non-inverting node. That's this one, right? And then now here is our feedback, right? So we have this coming back in, right? So we have a negative feedback there. This is a non-inverting amplifier with a negative feedback. The input V in is going to our non-inverting node. So that's how we get non-inverting amplifier. Okay. So when we have a non-inverting amplifier, which of the following represents the gain of the amplifier? So the gain of a non-inverting amplifier is 1 plus the feedback. So this is our feedback resistor, R2. So that's this one that's coming back here. So the gain is 1 plus this, right? So R2 over R1, the other resistor, right? And so this is A. So that's our answer, right? So this is just a formula for the gain of a non-inverting amplifier. So make sure that you remember this. And in other cases, maybe you would say the R2 being written as RF. It's just a feedback resistor, okay? So this is our answer. So A is our answer for 24. So moving along now to item 25. So item 25 refers to the following diagram. So let's look at our diagram now and see what are the key features. So we have our input voltage. This one is going into this node. This is our non-inverting node, right? The plus sign is our non-inverting node. So non-inverting node is the positive one, right? And that's where we are putting in our input voltage. So we have a non-inverting op-amp, right? That's what we're showing. So here we have our, what is this? Our resistance coming in. So let's call this our R1 that's coming in here and then going up. this is our feedback resistor. So this is RF, right? Because you see, it's taking from the output here and then coming back around to feed back in. So this is our feedback resistance, right? And this is our R1 that's coming in, right? Or R input, really, the resistance of the input, right? So now they're asking us the gain of the op amp in the diagram above. Remember, for question 24, right? For question 24, what we had done was show that this is the gain of a non-inverting amplifier. So 1 plus R2 over R1, right? And then down here, they're showing us a non-inverting amplifier and they're saying, okay, calculate the gain. So essentially have to use the formula that we got in 24, which is this, that the gain is equal to 1 plus R feedback or feedback 1 divided by the input 1, which is this, right? So we're going to do 1 plus 20 kilo ohm divided by 2 kilo ohm, and we get 1 plus 10, so that's 11. And so our answer here is 25, okay? So the first thing that you should do whenever you see any of these kind of like circuit diagrams is to look where your input is going. So you'll know if you have a non-inverting amplifier or an inverting amplifier, okay? So just look at where the input is going into. And in this case, it's going into our non-inverting node, which is a positive sign 1. So we know it's a non-inverting amplifier, which has a gain of 1 plus R over F. They give us RF. 1 plus RF over R. They gave us RF, so we can plug that in here. And the R in is 2 kilo ohm, so we can plug that in here. And we end up getting 11. So our answer is D. Okay? So moving along to item 26 now. Item 26 refers to the following diagrams, right? So here's our diagram. Again, guys, I said, whenever you see these circuits, these op-amp circuits, just like look where the input is going first of all, right? And you see here where they said this is our input voltage. It's going here. It's going in here. So it's going to our inverting node. So we end up with an inverting amplifier because the input is going into the minus portion, right? So this is an inverting amplifier. What else do I want to say about this diagram, or what else do you want to look at first? We want to look at the power supply voltage, and we see that the power supply voltage is plus 6, minus 6, right? So let's put that, let me tell you what that means. What that means is that the output volt, the supply voltage sets limit, right? Sets the limit on the output voltage that you can get, right? Output voltage possible, right? So that these are power supply voltage of plus 6, between negative 6 and plus 6 is what our output voltage can be. It can be anything greater than that, right? So it's gonna be from minus 6 volts. So the output voltage can be between that. So between any of those numbers, you can have your output voltage, right? All right, so keep that in mind. We have an inverting amplifier because our input is going into the inverting node. And then we have a power supply voltage here that kind of sets the limit on what the output voltage we can get. And then we have our feedback resistor, right? It comes from the output and it's feeding back a portion input into the input. So bam, bam, bam. So this is our feedback resistor here. And then of course, this is our input resistor, right? So we have all of those things and we've labeled them here. So let's see what the question is asking now. So they're showing us figure 2 here, right? So let's see, did they tell us what figure 2 was? Okay, let's look at figure 2. Figure 2 is showing us a input V in, so it's showing us our input waveform. So what we're inputting in has this waveform here, where it has a peak voltage of plus 2 and then the minimum of minus 2. It follows a sinusoidal wave, right? And the period is what? 0.02 seconds, right? So we have one complete wave in 0.02 seconds, okay? So those are key features to know. And the peak, so this is peak input velocity, right? Not velocity, peak input voltage. So the peak input voltage is this. Okay, so that's plus 2 volts. Okay, so I'm gonna write that there, plus 2 volts. Okay, so let's go up here now and see what the question is asking now. So the sinusoidal alternating voltage shown in figure 2, right? So that is applied to the input of the op amp as shown in figure 1, right? So we're gonna take this sinusoidal input voltage and we're gonna input that, we're gonna put that in to our inverting amplifier, right? So that's what we're doing here. And so it's saying that the voltage of the power supply is +6. And remember, we said that that kind of sets the output voltage, right? The output voltage can be higher than that. So it's important to note that our power supply voltage is +6. And that's just these numbers, right? That's the power supply voltage. And then now, the question actually is asking us which one of the following graphs correctly show the output voltage with time, right? So the output voltage is what we're trying to find, right? Output voltage. So let's come back. Let's see. Okay, so let's write down here, output voltage. How do we find output voltage? Output voltage, right? Output voltage is gonna actually be equal to your gain. So the gain of that amplifier, which is our inverting amplifier, times, we're gonna multiply that by our peak input voltage, right? And this peak input voltage we got from this sinusoidal curve, right? So peak input voltage. So output voltage is equal to your gain times your peak input voltage, right? So our gain of this inverting amplifier, remember now, for an inverting amplifier, which is what this is, the gain is equal to minus RF, the feedback resistor, over the input resistor. So we're going to do, the gain is equal to minus 8 kilo ohm divided by 2 kilo ohm, and we're going to come out with a gain of -4, right? -4. So what's going to happen now? If we have a peak input voltage of +2, so say we choose this as our peak input voltage, just starting out, we're gonna put in +2 here, and then the gain is -4, so we're gonna multiply that +2 by -4, and when we do that, we're gonna come out with the output voltage of what is this? 4 times +2 is going to give us -8 volts, right? And when we put in our output, when we put in a peak, when we use the -2 as a peak voltage, we're going to end up getting -4 times -2, and that's going to get us +8 volts. +8 volts, right? So what you see is that because an inverting amplifier, when you put in a plus voltage, you're going to end up getting a negative voltage. When you put in a negative voltage, you're going to end up getting a positive voltage. And that's what an inverting amplifier does. It inverts the signal, right? So let's say this for input. This is what input of -2. Right? So when you put in -2, we're gonna get an output of +8, right? So, okay, let's look at our graphs now. So we see that we get 8 here, guys. We got -8 and we got +8. But remember what I said, your output voltage can only be between -6 and +6, right? So this is gonna actually saturate out at less than -8. So it would be saturated at around -6. Right? And then this one will be saturated at around +6 because it can't be more than +6, right? So even though we calculated this 8, that just tells us what the peak would be if we could reach it. But we won't be able to reach it because our power supply voltage stops at 6, so we have to cut off at 6, right? So let's look at these answers now and see which one would fit those features, right? So again, our new output peak, it's an inverted thing. So this was gonna flip down to the bottom. So we should have this portion, this first portion should be now negative because it's -8, right? So it's gonna be going towards -8. And then this portion that was negative here is gonna flip up and become positive because it's an inverting. So if there are any waveforms that show this same sinusoidal pattern where it's positive and then negative, positive and negative, we can strike out those because it has to be inverted. That's the first criteria in looking at our graphs. It has to be inverted from here. So this wasn't inverted. It's still up and down and up and down. So we can strike out this. This isn't inverted either. It's the same up and down as here. And that's not what we want because it's an inverting amplifier. So we can strike out that. So we know A and C are not our answers, right? Now, if we look at B, we see that they're actually showing the peak being 8, right? Even though we calculated the peak being 8, guys, we can't show that on the graph because we won't see that in reality because our limits are between -6 and +6. So we have to strike out this, right? So this is inverted, so it captures the inversion, but it doesn't capture the fact that your power supply is limiting your output voltage, so you're not going to be able to say your peak is 8. No, this is not going to work, right? So let's look at C. So what's wrong with C? Let's look at C. So C is not inverted, right? So C is the same up and down, up and down. So we cross out C. C is not the answer. So then by default, our answer has to be D. But let's look at the features of D and see if it aligns with what we calculated and what we know, right? So if we look at D, we see that, yeah, they're showing that +8 -8 is what you would have calculated, which is what we had calculated, right? We got +8, we got -8. So they're showing that, so that's good. We capture that part. We capture the inversion because it's an inverted amplifier, so we have to invert this graph, and it captures that you, instead of having up, down, you know, have down, up. So they capture the inversion, and then they also capture the fact that your peak would be clipped, right? And it wouldn't go up to the +8, it would just stop at +6. So that's +6 here. And then the bottom is going to be -6. So you see that? This graph captures everything that we calculated and we know should be the reality. So this is our answer, guys, and I hope that makes sense. This is really a cool kind of an application of inverting amplifiers. And so let me know if you guys grasp this stuff and if it connects for you, okay? All right. So going down to item 27 now. So item 27 refers to the following diagram, right? So we have this diagram here. Our input voltage is going into the what? Non-inverting node, right? Because that's a +1, so it's not going to invert your input. It's non-inverting going in, right? And then we see that we have this feedback situation here, and then we have our output voltage, right? So what we actually call this kind of a circuit is that we'd say it's a voltage follower, right? And it acts as a buffer, right? So whenever you have high impedance sources, you can connect it to a low impedance load using a voltage follower. And the voltage follower acts as a buffer. And some other key features about the voltage follower is that whatever you put in is exactly what you're going to get out. There's no amplification really going on. It's just a voltage follower, right? So you put in I, you're going to get back out I here as your output. So V output is equal to V input. So what that means, guys, is that your gain is just going to be 1. Right? There's no amplification going on. It's just whatever you put in, you get back out. The gain is equal to 1. It's just acting as a buffer. Okay, so that's about the voltage follower in a nutshell. So let's see what the question is asking. The question is saying, which of the following statements does not, right? So which one does not apply to the op-amp in the circuit above? And again, we said this is a non-inverting op-amp. It's actually what we call a voltage follower, right? So let's see which one does not apply. The op-amp circuit is called a voltage follower. We know that this is the case. This is true, right? It's used as an inverter. No, guys, it's not going to invert. Why is it not going to invert? Because it's going into our non-inverting node. So this is not true. So that's false. And so that's actually our answer. But let's look at the other ones. The op-amp circuit is used as a buffer. So that's true. And it has a gain of 1. So that's true. But what's not true is that we're not using it as an inverter because, as you see, we're putting in the input into the non-inverting node, okay? So our answer is B. B is the one that's not true about our circuit, okay? All right. So moving on to question 28 now. So 28 is another logic gate question. And so what I typically tend to do for my logic gate question, I normally just write what the unit represents beside it so I know kind of what's going to happen, right? So this is a NOT gate, this is a NOT gate, and this is a NOR gate, right? So the question is asking us which of the following gates is equivalent to the combination above, right? So let's look at this is a combination, and we're trying to say, okay, if I put these three components together like this, will I get an OR gate? Is that the same as an XOR gate? Is it the same as an AND gate or a NAND gate? Which one is this equivalent to? Okay, so what I like to do for these questions is I would first try like a combination of input for all of them and see what you get, right? So if I had an OR gate, so let's just put in 0, 0 here, right? So let's put 0, 0. So that's my input. So let me write that. My truth table. A, B, C, right? So this is my two inputs, A input B, and then my output C. If I put in 0 and 0, I'm gonna get inversion here because it's a NOT gate, so it's gonna give me 1, and this is also gonna give me 1, right? When I come to an OR gate, if I had 1 and 1, I would have gotten 1, but because it's a NOR gate, it's gonna invert it, and so I actually end up with 0. So I put 0 here, right? Now let's look at the options that we have here. Which of these things would have a truth table like this for these inputs, right? So OR gate, for OR gate, 0, 0 would be 0. So we can say, okay, OR gate might work. For XOR gate, 0, 0 would give 0, 2. So our XOR might work. For an AND, 0 and 0 would give 0, 2. So a 0, so an AND gate might work. And then let's look at a NAND gate now. If I put 0, 0 in a NAND gate, what would I get? I'd actually get 1, right? So this is not gonna work, right? So it doesn't follow this truth table that I got from this. So this is not gonna work. So let's see now. Now we have to choose between these three, right? So let's come again. Let us choose between these. We're gonna choose between these three, right? So let's try another input. Let's try input in let me erase this, and we're gonna try another input, right? So let's try inputting in, say, let's do 1, 1, right? So we're inputting 1 here and 1 here. So I'm gonna put 1 here and 1 here. So it's a NOT gate, so it's gonna invert my 1 to 0. This is gonna invert my 1 to 0. And if 0, 0 is at an OR gate, it would be 0 ordinarily, but because it's a NOR gate, it's gonna end up being 1. So that's my truth, that's my second, that's my row here, right? If I put in A and B, they're both 1s, I'm gonna end up getting a 1, right? So now, which of these match that? For OR gate, if I have a 1 and a 1 going in, I'm gonna also get a 1, right? So that works for row 2. So let me put row 2 in a different color. Let me say that row 2 is blue, blue, blue. So this would also work, right? OR gate would work. 1, 1, I would still get 1. For XOR gate, if I have 1 and 1, I'm gonna get 0. So this doesn't work for XOR gate combination. This combination wouldn't be equivalent to an XOR gate because it doesn't work like that. XOR would be 1, 1, 0. So right, XOR doesn't work. For AND gate, of course, we know that if we have an AND gate and we have 1, 1, we're gonna get 1 because that's exactly how it works. So we know that the AND gate works. Okay, so now we're left to choose between the OR and the AND, right? So let's do another set of inputs and see what we end up with. Oh no. Okay, let me get back my pencil. Let me erase these, okay? So we're gonna test another set of inputs and see if we can eliminate either the OR or the AND, okay? So let's try, what shall we try? What should we try? Let's try 0. Let's try 0, 1. So we do 0, 1. So we do 0, 1, right? Inverting, so it's gonna put it to 1. This is inverting, so it's gonna put it to 0. And 1 and 0 at the OR gate would ordinarily be 1, but because it's a NOR gate, it's gonna be 0. So if we have 0, 1, 0, right? Let's look at the OR gate now. Let me put another color there. I hope you guys are following me along nicely. So this is 0, 1, 0. If we have an OR gate, right, and we have a 0 and a 1, that would give us 1 because OR gate is 1 or the other has to be 1 for you to get a 1. But we're showing here that based on this combination, if we put in 0 and 1, we're going to get 0. And that's not how OR gates function. So we can strike out OR gate. So OR gate is not our answer here. And let's look at AND gate now. Let's look at an AND gate, right? For the AND gate, remember now, for the AND gate, we need A and B to be 1 for us to get a 1. So if A is 0 and B is 1, we're going to get 0. You see what I'm saying? AND gate, we need two ones to get a 1. But because we have 0 and a 1, we're going to get 0, which is exactly what this combination gives. And so we know that this is a AND gate, or AND gate is the answer, right? So just sit with that one for a little bit and make sure that it makes sense to you. But essentially what we're doing is we're saying, okay, this is a combination of gates. Let's try some different inputs and see what our output would give us. And then now we can look among the solutions and see if this truth table would match any one of them. And it has to match at least one of them. And it turns out that the truth table that we got from this combination matches an AND gate. Okay, so that's how we got AND to be our answer. All right. So moving along to item 29. So item 29 refers to the following diagram of a half adder, right? So now we're adding these bits, right? So when we have a half adder, right, we can use a half adder to add two 1-bit numbers. So we can put in our input here. So say we put in 0 at this input and 0 at this input. At this OR gate, what we're going to get is the sum of these 2-bit numbers. And then down here at the AND gate, we're going to get the carry. But because we're adding 0 and 0, the sum is going to actually be 0 and the carry is also 0. Okay? So that's how half adder work. We have our A, we have our B. So these are our input 0, 0. The sum of those is at X, coming from the OR gate. And then at the Y, which is coming from the AND gate, we have our carry, whatever we carry over. So 0, 0. And if we put in 0 and 1, and we're asking the half adder to add those together, right? 0 and 1, the sum of that would actually be 1, right? And then our carry would be 0. Right? So we're just adding it. The sum is up here, the carry is down here. Now, if we're adding 1 and 0, the sum would still also be 1, but then the carry is 0. Right? So that's what we get down here. And then finally, if we're putting in 1 and 1, our sum is gonna actually be 0 and our carry is gonna be 1. So this is the only one that doesn't really follow your intuition as to what you would think, right? So 0, 0 is going to give a sum of 0 and a carry of 0. 0 and 1 is going to be a sum of 1 and no carry. And then when you have 1 and 0, of course, the sum is going to be 1 again, and then no carry. When you add in 1 and 1, you get a sum of 0 and a carry of 1. So again, just remember the key features of this half adder here. We have an OR gate, and from the OR gate comes our sum. We have an AND gate, and from the AND gate comes our carry. So just remember that, right? So that's a half adder in a nutshell. So let's see, go up here to the question. So it's question, where are we? This is item 29. So, okay, so here we are, right? So 29. So if A is equal to 1 and B is equal to 0, what are the values of the output X and Y? Right? So let's go back down here. If A is 1, let's erase these. So if A is 1 and B is 0, right, we're adding 1 and 0. And when we add 1 and 0, what do we get for our sum? When we add 1 and 0, we're going to get a sum of 1, and we're not going to get any carry. So carry is going to be 0, right? Remember this table that we just filled out, guys. So it's going to be 1 for your sum, which is at X, and your carry is going to be 0. So that's what we're looking for here. So we have a sum, which is X, right, of 1 and a carry of 0. So Y is 0. So X is 1, Y is 0. So our answer is C. Okay? All right. So 30 now. 30 is saying which of the following statements about RS flip-flops are correct? Correct. So RS flip-flop is a set reset flip-flop and it has two stable states. So that's just a quick revision on what RS flip-flops are. It has two stable states, right? It's a set reset flip-flop and it has two stable states. So which of the following statements about this RS flip-flops are correct? It contains two cross-link NAND or NOR gates. So this is true. This is how we construct the RS flip-flops, right? But the RS flip-flops, most commonly what you will see is you will see two OR gates, right? So you can either use two NOR gates, sorry. So you can either use two NOR gates that are cross-link or you use two NAND gates that are cross-link, right? So it's just kind of like a crisscross thing. So that's correct. That's a correct statement about RS flip-flops. The output is unpredictable for one combination of inputs. That's true, right? Because if we have like two high inputs coming in, so we have one going in one node and then another one, that's unpredictable. That's an unpredictable combination. So this statement is true. And then for part 3, it says it has two inputs and one stable output state. That's not true. It's a bistable device. It has two states. So if we say it has two inputs and one stable output, that's wrong, right? And so that leaves us with I and II being our answer, which is A, right? So this is just testing your use of knowledge on RS flip-flops and knowing what they actually are. They're made of two cross-link NAND or NOR gates, and the output is unpredictable for one combination of the input. So when you're putting in a 1 at one of the nodes and a 1 at one of the other ones, it's unpredictable. So that's the combination for which the output is unpredictable. And so this is true. This is true about it, and this is also true. This is not true because we know that RS flip-flops have two stable states. So this one is not true. Okay, so A is our answer. All right. So going down to 31 now, we're getting into module 3 now. So we're getting into the waves stuff, right? And all that good stuff around your particulate theory and so on. So which of the following phenomena both demonstrates the wave nature of matter? So we need to see some characteristics that are unique to waves, right? And so yeah, reflection and refraction are wave features, but in this particular case, when we're talking about like this kind of level of wave particle duality, we're most concerned with the interference and the diffraction. Those are the two phenomena that both demonstrate the wave nature of light, right? So that those are wave nature, interference patterns and diffraction patterns. So B is our answer here. Right? And of course, it wouldn't be line spectra is more like on an atomic level, right? So that wouldn't really work here. That's more a particulate kind of theory that it would support, that it would demonstrate. Interference would be of wave, but they want both to be related to wave. So this doesn't work, right? And then polarization and photoelectric effect, those would show the particulate nature of matter and not the wave nature. So that's not right. And then of course, this is not what we're looking for. We're looking for interference and diffraction because those are uniquely wave-related phenomena. Okay. So our answer is B here. So moving down now, in which of the following radiations do photons have the least energy? Right? So this is pulling on our knowledge of the electromagnetic spectrum, right? And so X-rays, we know are high energy. We know UV are fairly high too, and gamma rays are, of course, the highest. So the least among these would be infrared, because infrared is like way down, way to the left in terms of frequency, a very low frequency, right? So infrared, they have low frequency. So of course, they're gonna have low energy, right? And then the highest one of these would be this, right? So this is gamma. We know gamma is like to the far right. If we're looking at a spectrum ranked from low frequency to high frequency, the gamma rays would have a high frequency, and so they have a high energy. Okay, so they asked us about least energy, and so out of all of these, we know the least would be infrared. All right, so moving down to 32 now. So 32 says that photoelectrons are emitted from the surface of a zinc metal when light of intensity I and wavelength lambda is incident on it. So they're talking about the photoelectric effect. So the photoelectric effect is what this question is about. Photoelectric effect, right? So, all right. So we have a zinc metal, and we shine light of intensity I and lambda on it. Some photoelectrons are gonna get kicked off and they're gonna get emitted, right? So what is the effect on the work function, right, of the zinc metal if the intensity is doubled and the wavelength is reduced to a quarter of its previous value? So initially we have I and lambda, and then we're gonna double the intensity to 2I and then half the wavelength to quarter of what it was before. And they're asking us about the effect on the work function. Guys, remember the work function? That's just this phi, right? And we can write that the phi is equal to H times the what is this? What do we call this frequency? This is a threshold frequency. So that's what the work function would be equal to. But even more importantly is that you have to know what the definition of a work function is, right? The work function is like characteristic of a metal. So like zinc metal has a work function that is just related to zinc and nothing can change the work function, right? The work function is how much energy is needed to remove an electron from zinc, right? And that's a unique feature of zinc. And that work function is always going to be what it is no matter what. You can't change the work function of a metal. It just is, right? Zinc will just always need this amount of energy to be shined on it, or this amount of light to be shined on it for it to lose an electron. So the work function is not going to change. You can't change the work function, right? You cannot change the work function. It is intrinsic, right? It's intrinsic to a given metal. Intrinsic, or I would say set, or specific, right? Specific for a given metal. So you can't do anything externally to change it, right? You can't do anything external. It is what it is. And if you change the intensity and you change anything, wavelength, you're not going to change your work function. It's just not going to affect it. What this could affect, right, is the energy of the photons, or the amount of photons that you're hitting that metal with. But it's not going to change the work function, right? It's not going. The work function is set. It is what it is, right? So it's unchanged. 34 now. Electromagnetic radiation is produced when very high-speed electrons strike a hard target. This type of electromagnetic radiation is known as X-rays, because that's how we produce X-rays. We literally take high-speed electrons and we strike it against a hard target. And when we do that, that's how we produce X-rays. So the answer here is just gonna go straight into X-rays. That's how X-rays are produced, right? So that's what we're looking for here is B. All right, so 35, which of the following graphs correctly shows the relationship between the energy E of photon of light and their wavelength? So they don't show anything here, so this is not really a question, right? It's blank. So moving down to 36, item 36 refers to the following diagram. So let's look at this diagram together, guys. So we have a diagram here, we have electrons coming in, and it's gonna strike this carbon that's here. And then we're gonna get some spreading out, right? And then on the screen, we're gonna have some resulting patterns. We're gonna have like concentric rings of pattern, right? So we have an electron, the electron is coming in, banging on the carbon, and then we're gonna get some diffraction patterns, okay? Some concentric circles, that's what this ring pattern is, right? Okay, so let's see what the question is saying. A beam of electrons is made to strike a thin layer of carbon in an evacuated tube as shown in the diagram above. So we have electrons striking carbon, right? And so as I said, we're going to get some diffraction and some diffraction pattern, right? So let's write that this is a diffraction pattern, right? So earlier, remember we said that whenever we have diffraction or interference, what does that tell us about? That gives insight into the wave nature, right, of something. So this experiment is going to provide evidence for the wave nature of particle. Because when we do this, we get some diffraction pattern. So that would imply that electrons have wave-like properties, right? So that's what this means. It's an evidence for the wave nature of particles because we got diffraction, okay? All right, so 37 now. Object of mass M has kinetic energy EK. Which of the following is a correct expression for its de Broglie wavelength? So this de Broglie wavelength. We have to know what the definition of a de Broglie wavelength is first of all. So a de Broglie wavelength is given by this formula, which says that lambda, or your wavelength, is equal to Planck's constant divided by m times v, right? So this is just the velocity of that particle. So mass times velocity is momentum. So effectively, the de Broglie wavelength is equal to Planck's constant over momentum. So we know that this v, that this velocity, as it relates to these kind of particles or these kind of motion, right, within on a electron level, the velocity is gonna be equal. We can arrange this, the kinetic energy equation, which is half mv squared, to make velocity the subject. So we can find out velocity is, it's equal to 2 ek over m and just the square root of all of this. So that's v, right? So that's what v is this. So let me just use an arrow to show you guys. So this v, right, is actually given by this formula here for v, right? So now what we're gonna do, we're gonna take this v, right? Because they're asking us in terms of EK, you know, EK and an object of mass M. So that's why we had to go this route of saying, okay, EK is equal to half mv squared. So let me find what v would be. And then I'm gonna take that v and plug that in my expression for the de Broglie wavelength, right? So I literally then take this v and I say the de Broglie wavelength, lambda, is equal to h over m, so the mass, times the velocity that we just got. So that's mass, and that's raised to the power of 1, it's just 1. Multiply that by this velocity that we got from here, from our EK, from our kinetic energy expression. So I plug that in here and I get m times this term, which represents v. And when I simplify further, I'm gonna find that my m actually ends up becoming just half. So it becomes 1 minus this one, so it's m1, right? And you multiply that by the m that's down here, so it will be m to the minus a half. And so when I do that, I end up with this being just m raised to the half, right? So now I'm able to just move that m from outside into this square root sign. So that's why I end up with this. And so yeah, so when we look at these to see what matches our derivation, we see that this one matches it, right? So our answer is C. So what we're doing here, guys, is we're like, okay, let's start with what is the de Broglie wavelength, and the de Broglie wavelength is this formula. Then I'm like, okay, now they want me to relate to kinetic energy. So I'm gonna write my expression for kinetic energy and just solve for V. Then I'm gonna take that V that I get from my kinetic energy expression, I'm gonna plug that into my de Broglie formula. So I'm gonna end up with lambda is equal to h over m times this value of V, and then I just rearrange it to find what they want me to have it like this, right? So that's this answer here. So C is our answer. Hope that makes sense. Definitely drop a comment and let me know if it doesn't. So then 38 now. An isotope of nickel is represented by this, right? So it has a what? It has a mass number of 60 and an atomic number of 28, right? So which of the line in the following table correctly describes a neutral atom? So remember now, for a neutral atom, the number of protons and electrons are the same. So this number is the proton number. It will also be the same for the electron. So we should pick the answer that has the number of protons and electrons being the same, which is this one. See, number of protons is 28, number of electrons is 28, and that's the atomic number. So we know that that's right. And then of course, the number of neutrons would just be the mass number A minus Z. So that would be what? 60 minus 28, right? And that is 32 for our number of neutrons. So all of these line up and that makes sense. Our answer is B, okay? So moving on to 39, item 39 refers to the following diagram. So this is our stopping potential. This is our what? This is our threshold frequency. And then this is the frequency of our photon, right? So the threshold frequency, remember we said that that's what we use to calculate the work function. So the work function is gonna be H times that, F naught. So that's threshold frequency. And then this is gonna be the energy of the photon, right, that we're throwing at the metal. So it would be H is equal to H times Fa. That's the energy of a photon. And this is the work function of the metal that we're working with. And we're seeing our stopping potential here, right? So, okay, let's go down now. So in an experiment to investigate photoelectricity, a graph of stopping potential of the photoelectrons is plotted, right? So against the frequency of the incident radiation. So the radiation that hits the metal, right? So that's what this graph is showing. Stopping potential versus incident frequency. So the frequency of the incident radiation is what's on the x-axis, as we see here. So, okay. What is the maximum kinetic energy of photoelectrons emitted by the photons of frequency Fa? All right. So here's our general equation for this work function stuff, right? So the energy provided by the photons minus the work function is going to give us a EK max, right? So basically it's saying that if you shine a certain amount of energy on the metal, and that energy can overcome the work function, you're going to have some leftover energy, right? And that energy is going to be converted to kinetic energy. So that's what this formula is saying. This is my energy of my photons, this is my work function, and this is my EK max, my kinetic energy max. So remember from up here, I said that the energy of the photon is H times Fa, Planck's constant times Fa, and the work function is H times the threshold frequency. Yeah, so we come down here and we just plug those in, right? So E is equal to HFA, and then the work function is HF naught, and then the EK max will just be whatever it is. Of course, it would just be half mv squared because that's kinetic energy, right? But in the form that they want us to have it, they want us to put the maximum Ke in terms of these, and so it will just be this one, right? D, you see that? D matches our HFA minus HF naught. So that's our answer. Okay, guys? So that's just knowing the work function equation, which is this. So it's E minus the relationship between the work function and the energy of the photons and the kinetic energy is always going to be this. So just make sure that you remember this governing formula. This governs all things photoelectric effect, okay? So make sure you remember this equation. 40 now, for 40, they're saying that the mass of a nucleus is found to be 8.0032 units, and that of its individual constituent nucleus is 8.0045 units. So you see that there's like a little bit of a discrepancy with the masses here, right? This is slightly more than this. And so they're asking, what is the binding energy of this nucleus? Binding energy, right? So the binding energy of a nucleus is given by this Einstein equation, which is E is equal to delta mc squared. So as I said earlier, there's some kind of a difference between these masses. So that's this number here. That's this mass defect. And that's really what contributes to what this binding energy is, right? So that mass defect can be calculated as this 8.0045 minus 8.0032. And so we get a delta M of 0.0013 units, right? No. If you see that the value of energy that they want us to get is in joules, this is not SI unit, so we have to convert this U to kilogram. So to do that now, we come down here and we say delta M in kilograms is going to be equal to this amount that we got in units times 1.66 times 10 to the negative 27 kilogram, because that's the equivalent of 1 unit in kilograms, right? So we have 0.0013 units, and this is what the value is for 1 unit. So we will just multiply those through, and we end up getting 2.158 times 10 to the negative 30 kilograms. So that's our delta M, right? So all we have to do now is just plug this delta M back into this Einstein equation, So come over here and we do that over here, right? E is equal to delta M, which is 2.158 times 10 to the negative 30. And we're going to multiply that by the speed of light squared. So we do 3.0 times 10 to the 8 squared times that, times this delta M, and we come out with energy being equal to 1.94 times 10 to the negative 13 joules, and that's just B. Okay? So that's how we got B as our answer here. So what we have to go through with this calculation, but the key thing is knowing that you can relate the delta M, the change in mass or the mass defect, to energy using this Einstein equation. So this is what I would say, make sure that you're comfortable with this relativity kind of equation, right? So this is the key thing here. All right, so let's move on to question 41. So 41 now, we're saying that the decay constant of a radioactive sample of radon gas is this. So remember, decay constant is our lambda, right? If there were 1.6 times 10 to the 8 atoms of radon gas present at a certain time, so this is how much we have initially, right? So this whole thing, right? This is what we have at a certain time t, so that would be our N naught, what we have initially, the number of radon gas atoms that we have initially. And then, so they're asking how much time must pass before we end up with 1.2 times 10 to the 5. So this then is going to be our N final at a certain time t, right? So we can use this formula. This is your go-to formula, your key formula for these kinds of calculation, right? So N is how much we're gonna have at a set time, a certain point in time. N naught is what we started with initially, so that's 1.6 times 10 to the 5. And then of course we have E raised to the lambda times T, right? So the exponent of lambda T, right, is what we have here. And we have lambda, they gave us lambda. So we know everything here except T. So what we're gonna do is we're gonna just make T the subject because that's what we want to find. So to do that, we bring over the N naught. So that's what I did here, and then took the log of both sides. So I take the log of this side and the log of the right-hand side will give me minus lambda T. And then make T the subject now. So we're gonna do T is equal to ln. We're going to bring over the minus sign. So we're going to get minus ln times n over n naught divided by lambda is equal to t. So we're just plugging everything that we know. We know n was 1.2 times 10 to the 5. We know n naught was 1.6 times 10 to the 5. So we put that here. And then we know lambda is 1.1 times 10 to the negative 2 because they told us that from up here. So just plug in everything and we come out with time being equal to 28.76 seconds, which is the same as 29 seconds. So we're going to look in our answer for 29 seconds. And when we look, we see that that's B. So we select B, and B is our answer for 41. Okay? So the key takeaway here is make sure that you know this relationship that relates the N at any point in time to the initial amount and the decay constant. Okay? So make sure you know this equation. So 42 now, a nucleus of element A decays to form mendelevium, right? So we'll have A, and A is going to decay to form mendelevium. So we're going from A to mendelevium, right? And mendelevium has, what is this? A mass number of 255, and it has an atomic number of 101, right? So the way that we're going to go from A to mendelevium is when we do a sequence of 3 alpha emissions, right? Remember, alpha is 4 to He. So A is going to give out this 3 times in a row, right? And remember, whenever we have alpha particle emission, our mass number is going to decrease by 4 and our atomic number is going to decrease by 2. Right? So look at what I've written down here now for my kind of like a nuclear equation. We're starting with A, right? Which has an atomic number of A and a mass number, which is a mass number of A and an atomic number of Z, right? So A is gonna go to mendelevium eventually, right? That's what the question is telling us. So what's gonna happen is it's gonna do 3 alpha particle emission. So the mass number is going to decrease by 4 3 times, and the atomic number is going to decrease by 2 3 times, right? So we can write this A minus 4 times 3 is going to be equal to whatever the mass number of mendelevium ended up being. And then from an atomic number standpoint, Z, which is what we had initially, minus 2 times 3 is going to end up being what we got for mendelevium, which is 101. So Z minus 6 ended up being 101. So that means that Z, right, for A was 107. And then if A minus 12 is equal to 255, then that means that A for what we started with was 267, right? So effectively what we started with here is 267, 107, and then we ended up with mendelevium 255, 101, right? So this is what this little equation that I came up with here is telling us. So if they're asking us how many neutrons are in the nucleus of A, they're asking us about this. They're asking us about the element A. So to find number of nucleus, all we have to do is do the mass number, right, which is 267. We calculated that, and then minus the atomic number from that, and that will give us how many neutrons are there in the nucleus, and that is actually 160. So we select 160, that's our answer. Okay? So this one, the key takeaway from this question, I would say, is that know that when you have alpha particle emission, your mass number is going to decrease by 4 and your atomic number is going to decrease by 2. So if you have 3 of them, that's going to be 3 times 4. So 12, this is going to decrease by 12, right? That's what happened. And then down here, it's going to decrease by 2 times 3, so it's going to decrease by 6. So decrease by 6, we end up with this mendelevium. Decrease by 12, we ended up with this value for mendelevium mass number. Okay? So just sit with that one for a little bit, but just remember your different kinds of emissions that you can have, alpha, beta, or gamma, and just remember the changes that occur in mass number and atomic number per emission, right? All right. So let's move down to 43. So 43 is saying that a radioactive substance emits a type of ionizing radiation P, right, with the following properties. So if we have ionizing radiation with properties being that its mass is 0 and it moves at the speed of light right away, that tells us that we have gamma particles. Remember, gamma particles, they don't have any mass and they don't have any charge, right? But they are very fast and very high energy. And so they move at the speed of light, right? So this right away, we're talking about gamma here. So we just say, okay, all of this point to there being gamma, right? So then the question goes on to ask, which of the following statements about P is or true? So what about gamma rays? What's true about gamma rays? Is it true that they are not deflected by an electric field? That's true, because they don't have any charge and they don't have any mass. So they're not going to be deflected by an electric field, particularly the fact that they don't have a charge. The charge, if they had a charge, they'll be deflected by the electric field. But because they don't have a charge, they're not going to be deflected. So that's true. Part 2 now, P has a charge of equal to that of an electron. No, gamma rays don't have any charge. So this is wrong. And then for 3 now, P may be stopped by a piece of cardboard. No, gamma rays are very high energy. The only thing that can stop them is lead or concrete. So this is wrong. So the only thing that's true or right about our gamma rays is that they're not deflected by an electric field, and so only I is our answer. And so we select A, I only, right? I only, that's our only answer here, okay? All right, so moving down to question 44 now. So question 44 says that an archaeologist finds an ancient wooden relic and obtains its count rate as 20 counts per minute per gram of sample, right? The count rate from a bark of a living tree, right? So you take a living tree, you take the count rate from the bark of it, and that's 104 counts per minute per gram, right? And in the background, so what's just like anything or in the environment is going to cause some background radiation, that's equivalent to 8 counts per minute, right? So they're asking us now, what is the approximate age of the relic? An approximate age of the relic. So what we're gonna do effectively, guys, we're gonna compare the count rate of the relic to the count rate of a living tree, and then just kind of use that to figure out where is the relic in terms of its age when you compare it to a living tree. And so down here, they're saying that radioactive carbon, which is in all living things, right, has a half-life of 5,600 years. All right? So here's how we're going to approach this now. So we have a living tree that they say has a count rate of 104, right? And then the background count rate is 8. So we have to subtract out the 8 from that. So really, what the count rate of a living tree, a tree that's living, is going to be 104 minus 8. So that's 96 counts per minute per gram, right? Now for the wooden relic, we have to do the same thing. So we're going to subtract the background count rate of 8 from the 20. And that will give us a count rate of 14 counts per minute, right? Then we're going to say, oh, they gave us the half-life of radioactive carbon, right? And so for the living tree that has a count rate of 96, it would take 5,600 years for that count rate to drop to 48. So that's what we mean by half-life of radioactive carbon. So the living tree can go from 96 to 48, so half of its initial value in 5,600 years. So a count rate of 48 corresponds to something being alive for 5,600 years, right? So then it can also go through another half-life where the count rate would end up being 24 counts per minute. And that would be 2 half-lives, which is 2 times 5,600. So that's 11,000 years. So if something is alive for 11,000 years, it will have this count rate of 24 counts per minute. Now we can go through another third half-life where the count rate would end up being 12 counts per minute. And that would be equivalent to going through 3 half-lives, which is 3 times 5,600. And that would give it an age. At that point, it would be very old, super old, right? 16,600 years. And so what we see is that this 12 is very close to what the measured count rate of the wood relic is. You see, the 14 counts per minute is close to this 12 counts per minute. And we say if you have 12 counts per minute, it means that you're this old, you're this many years old, 16,600. And so because these are very close in their count rate, we can say approximately then that the age of that relic that had ended up with this count rate would be 16,600 years. And the closest answer to that 16,600 years here is 1,700 years. Right? I know that's a lot of math, but really and truly at the end of the day, what you have to realize is, okay, what is the definition of a half-life, right? The half-life is how long it takes for the count rate or the mass of the sample or the activity to decrease the half of its initial value. We have a count rate of 20 for the wooden relic, and we have a count rate of 100 for the living tree. So we can say, okay, let me find out at what year, given this, the half-life is 5,600 years for the living tree. Let's find out, right, how long it would take the living tree to get to a count rate that's similar to what the wooden relic is. And then that would be the age of the wooden relic. Okay? So just sit with this one for a little bit as well. It's a lot of math into it. But once you just go back to your fundamentals of, okay, what is a half-life and how can I relate the half-life to these count rates? Of course, you have to minus the background count rate. Always do that for sure. That's the first thing I did. But as long as you can relate back your count rate to the half-life, then you'll be able to do these kinds of analyses, okay? All right, so definitely sit with this one for a little bit. So 45 is our final one, right? And for this one, it refers to the following diagram, which shows a Geiger-Müller tube. So we have a Geiger-Müller tube here, and what this Y represents is our mica window. Mica window, right, is what this Y represents. And so let me just give you a quick recap on what the Geiger-Müller tube is. So we have this Geiger-Müller tube, we have a mica window. Well, So holistically, what we have is we have a cylindrical tube here, right? We have a cylindrical metal tube here, right? And the cylindrical metal tube, so this whole thing, right, the outer walls of it, so like here is gonna act as a cathode, right? So the tube itself is gonna act as a cathode. So that's what this X represents, is this cathode. The tube lining is a cathode. And then this thin wire that's along the axis of the cylinder, right? So this wire here, that's gonna go straight to our amplifier and counter. This one is our anode, right? So we have a cathode and an anode in the Geiger-Müller tube. The anode is the center thin wire. The cathode is a cylindrical tube. And then we have a mica window, and it's through the mica window that the ionizing radiation is gonna enter, right? And then it's gonna come in, and then the electrons are gonna accelerate towards the anode, and then the positive ions are going to go towards the cathode, and then you're going to be able to come up with some count rate in a nutshell, right? That's how the Geiger-Müller tube works. So again, this little thing here at the beginning of the cylindrical tube is our mica window through which the ionizing radiation will come, and then this is our cathode to which the positive ions are going to come. And then this is our anode to which the free electrons are going to migrate, right? So this is our anode. It's just this thin wire in the middle here. So that's our anode, right? So let's see. What are the parts labeled W, X, and Y? So what did we say? W is our anode. So that's here. X is our cathode. That's the tube itself, the cylindrical tube. It's X. So that's the cathode. And then the Y is our mica window through which the ionizing radiation is going to go. So with that, guys, we've gone through all 45 questions on this specimen paper in great detail. Definitely make sure that you sit with these for a little bit and like really wrap your head around it and see what equations you should remember. And then, of course, any comments or any questions on anything that we've done, definitely drop that down below. Please like this video. Please subscribe to this channel, and I'll see you in the next video, and all the best in your paper 1 exam. And thank you so much for coming along this journey with me, okay? All the best in your exam.